Okay, let's discuss about keratometry. Today, discussion topic is keratometry, and it's very fascinating procedure. So basically, keratometry is an instrument that designed to measure the radius of curvature. Definitely, we measure radius of curvature, and after radius of curvature, we convert it to the power, isn't it? And the refracting power of the interior surface of crossed fixed chord of diameter approximately, so we measure approximately central 2 to 3 mm, okay, which lies in the optical spherical zone of the cornea. So at that particular zone, at that 2 to 3 mm of cornea, the center is, we consider that it's a spherical zone. Yes, definitely it is, moreover it's spherical, though cornea is definitely a spheric, but we consider 2 to 3 mm zone is a roughly spherical surface. So we measure radius of curvature and we convert radius of curvature to directly power from the conversion factor. So optical principle of keratometry is basically cornea, front surface of cornea, we can consider it as a concave mirror. Okay, not a concave mirror, for God's sake, convex mirror, definitely convex mirror, not concave mirror. Okay, so the front surface of cornea is that why for front surface is because we measure first frequency image size, isn't it? The optical principle used for the class of instrument is relationship with the first frequency image size to the radius of anterior corneal surface, because we measure the image of first frequency image when we project the object. So comparing the relationship between size of an object and the size of the image of the object reflected from the convex mirror. Convex mirror of what? The front surface of the cornea is convex mirror, and that's virtual and behind the mirror, as we know. So I want to discuss it drawing myself, and then we will discuss again. Let's take an example. Let's make it. This is the front surface of the cornea, and this is the optical axis. Consider this is the focus. Okay, this is the focus, and consider this is the center of the rotation, which is C. And consider this is the object, that's Meyer we are projecting. This parallel surface from optical surface, this is the parallel. Whenever parallel line goes, we know it focuses on the focus. So that's the point, isn't it? And whenever a single line comes to C, then it goes without a deviation. Then that's where image is formed, isn't it? It's very simple. That's object height, that's image height. Image height is as dash. So object distance, we always consider object distance is u. Image distance from the vertex, let's consider it as a whatever you want. I think image distance v is always better. So as the magnification formula, object height divided by image height is equal to object distance divided by image distance. So what we want here, we want to know the radius, isn't it? So let's consider image distance, that is v, I think equals to f if we consider object at infinity, far distance. So let's consider that, because uh, here image is here and the focal point is, there is very few gap. Let's consider it that object at infinity, then image distance is equal to f, isn't it? And what is focus in case of mirror is basically r by 2. We know it, isn't it? So so what v is actually, we can replace it with r by 2, isn't it? Yes, object distance, yes, just image object height, image height, you object distance divided by r by 2. Then what we are actually interested is basically to finding r, isn't it? Radius of curvature of the mirror. And what is mirror? Front surface of the cornea. That's why r is, so basically what is r? R is 2u h dash divided by h, isn't it? So let's think about this formula. Let's once think about this formula. Let me write it, this formula. R is equal to 2 u h divided by H dash divided by H. What we have, we know U, object distance, we already know. We know object height, isn't it? Yes. The only thing in this equation that we don't know is H dash, the image height. If we know image height that as dash, then we don't have any problem. We directly get R, isn't it? So the only thing that is important and that we have to investigate is the as dash. That is was what's that mean? That means image height. Okay, this is the formula you must know, and this is the way you draw diagram and you plot the scenario and you just derive the formula. Okay, this is the final formula. So so this is what I have driven here. Okay, so don't worry about it. So basically image height and image, there are a lot of things. As long as image is focused, d is constant between these three, and r is a function of object and image. So that's assumption is distance between object and interior surface of the coordinate is relatively long. I have taken as infinity. That's why virtual image is located close to the focal point, and I have taken that. Yes, object image distance is actually focal point. So that's the consideration. Okay, optical principle of keratometry. So only thing that we have to measure is image height, isn't it? So due to the one, and there is a problem. Due to the presence of involuntary miniature eye movement during the eye fixation. Why involuntary movement? A miniature eye movement is very important for the eye, isn't it? Remember the visual perception class, if you remember that, then the Toxler phenomenon, and you will get the answer. Why involuntary miniature eye movement is very important for our. We think that our eye is stable, but it's not at all. So it's basically nature needs it. That's why. Okay. So if I have miniature movement, then we have to measure the image height, but it's quite difficult. That's why we develop doubling principle. So the image formed by anterior cornea also moves if eyes moves, and it's not possible to measure. That's why to overcome that obstacle, doubling principle is invented. So what is basically doubling principle? So there are a lot of things you'll come to know in keratometry, but what is doubling principle? That's very important, and the different type of doubling. Yeah, there are a lot of things. Okay, so doubling principle is to use the prism to double the image of an object. Basically, that's the simple thing. Why we do that? Because prism is moved along the optical axis until two images are just touched. Okay, just remember that two images just touched. Thus what happens if two images are touched? First prism made two images, then we move that prism along the optical axis so that that two images just touch. Then what do you mean by that two images just touch? If that two images just touch, the prismatic displacement for touching that two images is equals to the image size. That's the game here. Okay, the larger the image size is, the greater the amount of doubling, the greater would be the prismatic displacement. This is the great line that you can write in your exam as an student. What is doubling? Okay, so see, first you do the doubling because prism, and you move that prism in an optical axis. This is the optical axis, isn't it? Then you move, and whenever that two wires just touches each other, that displacement is actually doubling. That displacement is actually size of the one wire, and we will get the height of the image. Okay, so optical principle instrument is rotating wheel is moved to the prism. Amount of prism displacement is equal to amount image size, the correspondence of radius of curvature, and calibrated to rotating wheel, and we know that. So there are four types of doubling. I will go briefly. Fixed doubling, variable doubling, divided doubling, full doubling. So fixed doubling means fixed object height, and doubling devices system, variable image size and Meyer separation. These two things are variable, image size and Meyer separation. Variable doubling, fixed Meyer separation and image size. What is variable? Variable distance of doubling devices and variable object size. That's variable doubling. So divided doubling is the telescope objective is divided into two separate fields. This transmit only the portion of the incident beam reflex. That's why divided. Okay. Full doubling. The doubling is achieved by the aid of full aperture beam splitting device. Okay. The dividing doubling and full doubling, that's another story. Just remember that it's fixed doubling and variable doubling. So I don't know how many times these doubling questions asked in the exam. I don't know. Just remember these things. Okay. So optical principle of keratometry, and I just wanted to show you one picture. That's why I have just put Boston lump. That constant object size and utilize different images and image doubling using vertical and horizontal simultaneous prisms and light coming from the object and reflect from the cornea. See, this is the picture I want to show. So this is examiner's eye and this is patient's eye. Okay, we put Meyer here, and the reflection of Meyer in a patient's eye goes from here, and then it comes to uh, what do you call it? It comes to objective lens, and there is a aperture diagram, and this is the doubling principle, and the doubling prism made the image here is a double. This is one, this is another, this is the central image. So, and this is eyepiece, and which definitely objective and eyepiece makes telescope, and we will see magnified image by the examiner. This is how the optical system works. Okay, so procedure is very basics, but I'm not going to talk about procedure by focusing just on procedure. Okay, you read the procedure and you do in a clinic, then you understand what is procedure. But procedure, I think procedure cannot be teaching by these videos or anything. Okay, procedure you have to go into lab and work. So procedure focus the eyepiece, which is very important no matter what. If it's keratometry or if it is lensometer, just or if it is slit lamp, just focus the eyepiece and position the patients and instruct them, adjust the instrument and locate the principal meridian, which is very important. Don't just going to focus there, make the instrument and record the measurement. Okay, so there, and sometimes you see one position keratometry and two position keratometry. It's very simple. Okay, one position keratometry means you can measure directly in not changing the position both meridian. That's simple. Okay, so simultaneous doubling perpendicular pair of Myers produce doubling device in each corresponding principal meridian and simultaneous measurement in the both meridian. So it means basically simultaneous measure, you can measure simultaneously both meridian. You don't have to rotate the machine. That's simple. Two position means you require rotate the axis of the axis to measure the each meridian. So two position means you have to move from one position, you may measure one meridian, and then you have to move the instrument, rotate the instrument up to another meridian, and you measure another meridian. So in two position means only one position can be measured, only one meridian can be measured at a time. One position means both meridian can be measured at a time. So, what are the source of error in case of keratometry? First, faulty position. I have seen a lot of students doing that. Faulty position of the patient. Okay, and patient is not at the chin and head is not raised and properly not aligned. So lack of fixation of the patient, and it's always there. And whenever patient has dense cataract, so it's always there. So it's better to instruct patient correctly. If instruction instrument is not correctly focused or operation accommodate during the measurement, and image may be more displaced from the intended location, thereby causing error. It's always there. Just remember these things. Okay. Localization of corneal and distortion and excessive tearing and abnormal position of lid. It's always there. Abnormal position of especially lid is drooping or excessive tearing, which causes maybe like too much stiffening of the Myers. Improper focusing on corneal image. That's the source of errors. Okay, and this is important concept, and this is very important, and it will be asked in your viva a lot, and it will be very important in facing MCQs too. Okay, so normally the range of keratometry from 36 diopter to 52. Steepest is 52 diopter, and flattest is 36 diopter. What if cornea is 30 diopter, cornea have 58 diopter? What if it goes beyond the range of normal cornea, and then we have to expand the range of normal keratometry? Sorry, that expanding the range of normal keratometry is basically what we are trying to do. So if k reading is very low and very high, for high we place 1.525 diopter trial lens over eyepiece. So if we put 1 plus 1.25 trial lens over eyepiece, then it increases our range by 9 diopter, means 52 plus 9, which is 61 diopter. Up to 61 diopter we can measure. Okay, another factor is we can measure k value by 1.25, and whatever it has we can multiply by 1.85. Just remember this factor, 1.85, 1.185. Sometimes it's asked in MCQ. Okay, suppose example 1.25 is we put in the eyepiece and we dial 49 diopter. Actually it's 49 diopter is 49 into 1.185, which is absolutely 58 diopter. That's how we calculate. So that's why it is called correction factor to 1.185. So it's very important to understand this point, and sometimes ask how much diopter we have to add, which is basically 9 diopter. Sometimes MCQ asks how much power plus power we have to add, which is 1 plus 1.25. At the same time it's very low, then we will place minus 1 diopter trial over eyepiece, and the shift decreases by 6 diopter, increases by 9 diopter, and we have to place plus 1.25, decreases by 6 diopter, we have to place minus 1.25, and the multiplying factor is 0.84. So it's very important. Okay, reading dial is 38 diopter, then what will do, 38 into 0.84, actually cornea is this. So it's sometimes called extended keratometry. So it's very important you understand these things. It's very important you understand how much we have to add, how much is shift there, and what is the multiplying factor, because in MCQ, and sometimes MCQ asks like this: you do this, you put minus 1 and there's this value, and what is the actual value, then you have to know this from this value, then multiplying this to 38 into 0.84. In case of plus, I think 1.185, isn't it? In case of minus, 0.84, reducing. That's very important, these two things. Okay, so corneal versus refractive astigmatism. So here we comes Javal's rule. So it's basic, very simple. Refractive astigmatism is corneal and internal astigmatism. Internal astigmatism is due to toricity of back surface of the cornea, tilt of crystalline lens with respect to it's maximally it's against the rule astigmatism, isn't it? So Javal's rules tell you the refractive astigmatism is this: is corneal astigmatism plus p into approximately 1.25, and the k is equal to 0.5 and 180 degree. So which is basically we think it's a mean internal astigmatism, isn't it? So internal astigmatism is against the rule astigmatism. So basically Javal's rule, just see this Javal's rule: corneal astigmatism and prediction of total astigmatism. If corneal astigmatism is minus 2 at the rate 90 degree, then it's just 1 degree, 1 diopter higher, isn't it? 1 diopter is 0.7 diopter higher. 0 it's against the rule astigmatism. Minus 1, sorry, yes, minus 1 it reduces, isn't it? Minus 3 at 180 degree, it's what if 0.2. So total refraction and it's a relationship. This see prediction of total astigmatism, and see corneal astigmatism. This is against the rule from 0, this is with the rule from 0, and just see if it is 0, then it is this. It's simple, it's against the rule astigmatism, it's with the rule astigmatism. Just see this. Okay, so basically simplified form of Javal's is, see, for all the three subjects that are found in straight line having the question, refractive astigmatism is this: 1 into keratometric astigmatism minus 0.5 into 90 degree, and that's, just remember these things. Okay, so this is also, pause the video and see the correlations. Okay, so improving keratometric accuracy, this scientist said keratometric finding tends to be less accurate with the vertical meridian than horizontal meridian. Variation of 0.19 diopter horizontal meridian and 0.38 diopter vertical meridian using Boston keratometry. And possible causes of inaccuracy is vertical doubling or the minus sign of the image when instrument is out of focus, and drooping of eyelid, and one of the minus sign is disappeared, that's why they are more inaccurate. So improving accuracy, so how to track it: use the plus sign to mirror image to both horizontal and reading, because plus signs there is high chances of stacking plus sign and plus sign, there is high chances of uh, getting less inaccurate measurement. Or modified the plus and minus signs of the keratometry finding can be vernier alignment rather than just not superimpose them, but do the vernier alignment, because our eye is very good with the vernier acuity. So clinical uses are contact lens base curve selection, isn't it? Detection of RGB flexure, detection of deposits irregularity and poor weighting, detection and monitor of corneal surface distortion, estimate refractive astigmatism, differential diagnosis of refractive and axial anisometropia, diagnose and monitor the keratoconus and corneal disease. Nowadays, corneal topography doing fantastic job. So calculation of IOL power is still relevant today. So monitor intrasurgical or post-surgical astigmatism. Okay. So these are the references. Yes, definitely this is a great book to read. Keratometry. Just remember, this is the great book to read, Keratometry. Okay. So I think Bistan choose.